visible on the back? Clear? You can all see. Okay, so it's getting a little cut off. Well, if it becomes a problem, let me know. But we won't be using PowerPoint too much, so it'll be quite a bit of Blackboard and work and discussions. Maybe when I need to bring up some pictures of experiments or some other things, I might use the computer. Mostly we talk to it. Okay, hello. I'm Gurudev Sir. I'm going to be teaching the special topics course on quantum optics and quantum information. So right now, of course, as you all know, quantum computing, quantum information, quantum communication is an extremely hot research area. Many of you are probably, I think I see some of you are all graduate students here at Pitt are working on this topic. And so we'll go around a little bit, and also I would like to get to know you and learn what you're working on and what you might be interested in hearing about. But before I do that, I've passed around the syllabus for the course to everyone, hopefully. You received it. So I'll just quickly go through the course organization. Fairly straightforward. We'll have lectures here, 11 to 12:15. If I have to cancel sometimes for reasons of travel, etc., then or sickness, I'll let you know hopefully in time, and then we might have to have one or two catch-up lectures later on at some time that's common to us. Okay, so a lot of the information is now available on the website, courseweb.pit. The syllabus is also there if you want to look at it there. The main way in which we will assess your work in this course is through the homework. Homework assignments will be posted each Thursday, typically due the following Thursday. And I'll accept late homeworks, just give you 10% penalty for each day. Okay. With homework, since the largest portion of the results in this class are from the homeworks, I expect you to do them independently. You can talk to other students, but write up your solutions independently. The other part of your assessment is on a final project presentation and a written report on some topic, typically of some very current research area, either in quantum optics or quantum information. I will, grade all those based on and I'll assign those topics later on in the course. Okay, so recommended textbooks. The final grade is computed 75% as a homework, 25% presentation plus a grade. Okay. The lectures, as I said, are going to be the main part of this class. Are going to be mostly on the chalkboard. They won't follow any one particular textbook. I'll be taking different sections from different textbooks as needed. Whenever I am referencing a particular text, I'll try to be careful and point it out, but I might forget. If you are not sure, you want to read it up more in detail later, let me know. I'm also going to try and provide you with the written lecture notes whenever possible. But I can't promise every time that I'll do that, but I'll do my best. As I said, the textbooks, the first three in this list, Elements of Quantum Optics by Meister and Sargent, Quantum Optics by Walls and Milburn, and then Fundamentals of Quantum Optics and Quantum Information by Lambropoulos and Petrosian. These three textbooks are actually available for free online with the Pitt Library, so you can go online to read them. You don't need to buy them. Then there are these other four books down here. One is sort of like very important book in the field, which is Quantum Optics by Scully and Zubairi. I'll probably follow that also for some very important sections on open quantum systems. Then there's a recent couple books. This book, Quantum Optics by Mark Fox, is a nice, I would say, a little bit more undergraduate level presentation. So if there are some aspects that has been a while since you've looked at, or if those are some aspects that you would like to look at a slightly lower level, then you can look at that textbook. It has a lot of the important concepts and physics, but maybe it doesn't have as much of the rigor of details that you might need to follow some graduate level work. And then finally, the last two parts, which sort of indicate, that the last 1/3 of the course is on quantum, or maybe slightly more than that, is on quantum information, right? This course is quantum optics and quantum information. So we will be discussing those from those textbooks. This is the Bible of quantum information textbooks, Nielsen and Chong. Not the greatest book, but still it is the Bible, so I put it out there. It is a little bit hard to follow at times, and but it has an exhaustive amount of material. And then the other book which I like is Quantum Computer Science by David Burton. So between all these books, I think you have plenty of references, textbooks to look at, to supplement the course notes. And so let me then tell you a little bit how I've sort of decided to cover the material. And if you look at the course schedule in your syllabus, I kind of give a week by week outline of what I'm planning to cover. Okay? And so I should mention that although I have put a lot of topics here, I probably will not be able to cover, given the sort of the week by week outline, I won't be able to cover every one of these in detail in the class. So I'll try to cover parts of them which I've deemed the most important. For the rest, I'll give you supplementary notes to read on those aspects so that you have them, but I may not go into all the details of the derivation in the class because it becomes hard in the class to go through every equation and every step. But I'll try to supplement it with my notes and so on. So to begin, we are right now in the first week. We're going to do introduction and overview, and I'll probably launch into the review of quantum mechanics almost right away, and the classical optics. And then, as shown here, we'll go through first the probably the thing that you will most encounter in many any graduate level work or PhD level work, which is you have to understand the fundamental semi-classical treatment of an atom interacting with a classical field first. Okay, so we'll go through all that, which involves all these different topics, some of which you've probably seen, like Rabi oscillations and spin resonance, but then we'll generalize to multi-state systems. We'll talk about dress states, adiabatic passage, and adiabatic elimination. And then I'll cover a little bit of the initial basis of quantum information science, which is quantum state engineering, things like block sphere and entanglement and qubits. I'll introduce that probably somewhere in there. And then we'll get into sort of the quantum treatment of atom field interactions, which involves things like understanding what a photon is, what is field, how do you field quantize the electromagnetic field. You've probably seen that maybe in some other places, so we'll go over some of that quickly. Maybe I'll just give you notes to look at that in detail, and we'll try to talk about the more important things which you might not have seen, which are things like the states of the electromagnetic field, Fock states, coherent states, quantum states of the electromagnetic field. And then we'll discuss things like Wigner-Weisskopf theory of spontaneous emission and Jaynes Cumming model, which are very fundamental to understanding current research in quantum information as well. And that will then, I'll come to a very theoretical section, which is these two parts here, which are kind of very important to understand basics of decoherence, dissipation, and so on. But they are very theoretical, and so we might go over some of that material more at a high level and keep some of the details of the calculations for either homeworks or for lecture notes. I'll try to give you the big, picture view of these things. They are important if you're ever trying to follow any actual calculation in a quantum information or quantum optics paper. But it's probably more important to know when they can be applied, when they sort of fail, which formalism is more expected to be applied in certain situations as opposed to other situations. And then the details of the calculation obviously are something that you just have to really, plug through when you want to understand it. So, but we'll go through all of that. And then, and that this is basically, this last part is essentially a continuation of the open quantum systems. In the quantum treatment, we'll discuss all the important cavity QED effects, which if you don't know what that means, don't worry, we'll come to that in this class. And then discuss some quantum dynamics using Heisenberg, Langevin formalism, homodynamic detection, etc. Finally, the last, as I mentioned, 1/3 or 1/2 of this class, I'm going to discuss quantum information processing. We've already seen some basics of qubits, but then we'll talk more about the important logic elements such as quantum logic gates, quantum circuits, and then the basic or the most important algorithms that are there in quantum information processing, such as these, the ones that are outlined here, Deutsch-Jozef-Simons problem, which is the first sort of non-trivial quantum algorithm, quantum Fourier transform, which is also a very important component of things like Shor's algorithm. And if we have time, we'll go through some of these other ones, like quantum search and quantum cryptography. Let's see how far we get. And then, as I said, if we can't cover everything, what we might do is assign some of those topics to the project presentations, for example, and have you guys present that to the class. Okay, so let's talk about the first. Any questions at this point? Okay, sort of ambitious plan. Hopefully we get through most of it in this class. Okay, so I decided to sort of first give a little bit of background to quantum optics, which is a sort of a history of the field. And when you look at the history of the field, in fact, as we know, light and quantum mechanics have a very, very long connection, a very important connection. That in fact it was by trying to understand the properties of light emission and thermodynamics of light emission and absorption that many of the fundamental properties of quantum mechanics were first realized. So, for example, Planck, when he was trying to understand the thermal radiation, the electromagnetic spectrum that was emitted by a black body, that's how he first came up with the connection or the idea that light must be emitted and absorbed in discrete quanta, which he didn't label them, but which are now we call them as photons, right? And Einstein was the next person who said that these quanta, so the difference between Planck and Einstein maybe could be summarized as Planck said that the emission and absorption process happens as packets of energy, and Einstein said no, the actual packets are actually packets of the light, the radiation field. So he said really the radiation field itself is quantized, is not just the emission absorption process itself, but in fact the actual packets of light itself that is quantized, if you like, as a very sort of hand-waving way to explain the difference, right? And from that insight that the electromagnetic field or light itself comes in these packets, and it's not just the interaction with atoms that is quantized, he derived very important phenomena such as the equilibrium between matter and light, and then also, of course, a very important effect such as stimulated emission, which gave rise to things like lasers, and of course the photoelectric effect for which he won the Nobel Prize. And the word photon itself did not arise till about 1926 by Gilbert Lewis, who coined that phrase. So again, the key role of light itself in the development of quantum mechanics, in terms of atomic spectra, that is the other reason. To understand the quantization, they had to understand how light interacts with atomic systems. And that is, of course, the basis of the work of many of these famous scientists: de Broglie, Schrodinger, Dirac, Fermi, Born, etc. One of the puzzling aspects of quantum mechanics at the beginning was spontaneous emission. Why does an atom, which is in a eigenstate of the energy, right? It's an eigenstate of the Hamiltonian. If it's in an eigenstate, it should live there forever, but it doesn't. It emits spontaneously, right? So this is an important question that was addressed by Weisskopf and Wigner, who derived the decay rate of an atom, which is coupled to the electromagnetic field, but they use non-relativistic quantum mechanics to describe the spontaneous emission process. I don't remember when that paper came out. You can look at that. And that led to the development eventually also of quantum electrodynamics, right? Which is a fully quantized version where everything is treated quantum, including the electrons, and so on, etc. And if you want a little bit more rigorous definition or sort of categorization of where is classical optics, where is quantum optics, where is quantum electrodynamics, I'll come to that a little bit later in the class. We can draw it actually on a nice diagram where all the regimes of quantum optics and quantum electrodynamics apply. I'll come to that. So when we think about this quantum optics, as I said, which is a little bit hard to define, it actually is in a very sort of narrow regime, as I'll show you in a little bit, where people wanted to talk about quantum optics as a separate subject, which is different from fully quantized relativistic treatment, which is quantum electrodynamics, right? Which is fully quantized and relativistically invariant or covariant. That is quantum electrodynamics. But for a lot of phenomena in the lab, we don't need that full quantum relativistic treatment to understand phenomena. In fact, it's too much, right? The machinery of QED would be just way too hard to apply to a lot of phenomena in the lab. So in the 1950s, there were some experiments that first started to make people think about what really is quantum optics, which is this understanding of the theory of detection, photo detection. Okay, seems like a simple thing. You send photons into a detector, it produces an electrical signal, and that electrical signal is proportional to the intensity. And that's how we always think about it. But when you actually look deeper into the problem, it turned out to be quite subtle. And it took almost till the 1950s that we finally came up with a fully quantum theory of photo detection and of the coherence, the property of the electromagnetic field that we call coherence, to understand all of these quantum states of light that are just produced in a lab, which don't require like a fully quantized and relativistic treatment of electromagnetism and particles and everything. Okay? So, as I said, these experiments, the Hanbury-Brown-Twiss experiment is one of the most famous experiments, which we will cover later on in the class. They looked at the correlations between two detectors. So they had two detectors that were measuring intensity of the light, and they looked at the correlations between these detectors, and they found something very interesting. They found some correlations that could not be easily understood. They saw things like bunching of photons. Eventually people saw also things like anti-bunching. All of these important statistics of these correlations had to be understood, and they were not understood until we had a fully quantum theory of the coherence of light, which was pioneered by Glauber and Sudarshan and Wolf and Mandel. Okay, and Glauber won the Nobel Prize for that work. Also, the coherence turns out to be important when you think about light-matter interactions. So when you consider an atom that's driven by a coherent light field, it undergoes certain behavior that is kind of non-intuitive, which is Rabi oscillations and things like Ramsey fringes, and all of those effects required some explanation, which came fairly quickly, but are also part of what we consider as the quantum optics part, because they are low energy. They don't require the fully quantized treatment of both or relativistic treatment of electrons and positrons to understand. So all of these developments in quantum optics, which included the understanding of the states of light, along with better understanding of things like spontaneous emission, which was at a very sort of, if you look back now, it kind of seems like a very simple understanding that we had at that time of what spontaneous emission is and things like that, when Einstein came up with it. But eventually, this led to the developments of, along with improvements in materials and so on, led to tunable lasers and lasers in general and tunable lasers. And that led to a big flourishing of quantum optics. Lots of experiments that had previously not been possible. So you have to understand, till about like the 1960s and 1970s, we didn't have lasers. So a lot of the things that we take for granted now, when we think about like, fluorescence or the being able to scan across a laser and scan across the resonance of an atom and look at its spectrum in fluorescence, and many of these things were enabled by production of things like tunable light sources and tunable coherent light sources like lasers. So as I mentioned, the non-classical light states, which had previously not been thought about or observed, were finally observed by Kimball and Mandel, and then the theory was carried out by people like Walls and Carmichael and Coulter. So this is sort of up to the 1970s, and then up to the 1980s that led to another flourishing of things like nonlinear optics, parametric down conversion, which is one of the main ways in which we first started to verify many of the predictions of entanglement by Einstein, Podolsky, Rosen states. That many of these things were observed in these initial experiments. For example, something that's not here but is left out is by the experiment by Aspect, where they actually did the first experiments to show that EPR paradox, or the EPR Bell states and the Bell inequalities were measured using these kinds of ideas of cascades of atomic states and so on. Okay, and then we have, as I said, in the 80s, squeezed light, the first sort of another type of non-classical light state, which we'll also cover in this class, was demonstrated. And then came the big sort of experiments which involved things like atoms being coupled to cavities. And this is like saying that we have now control of both a single atom and a single photon at the quantum level, and we're observing sort of the interchange or the interplay of quantum states and quantum information between these objects, and that led to some very beautiful experiments. Haroche carried out these experiments in France with microwave cavities and atoms, and then the similar experiments were carried out with atoms in optical cavities by Kimball and Rempe. And this led also along with developments in trapped ions to sort of the big successes. Here we have sort of the violation of Bell's inequalities that was verified by those people, Clauser, Aspect, and Zeilinger, based on those developments in the early 1980s. And as you can see, a number of Nobel Prizes and prestigious prizes in physics have been awarded to these other developments that have come out of understanding quantum optics and atomic physics and laser physics better and better. I've left out here sort of the more recent ones, like 2016, or I can't quite remember the year, but when, for example, things like the laser cooling, quantum control, and quantum computing in ion traps was done by Wineland and Rainer Blatt and Peter Zoller. So those people, that led to sort of now this flourishing in also quantum computing that we are seeing right now. And I obviously left out a lot of developments after that, including things like various superconducting qubits, solid state qubits, etc., etc. Okay, one of the things, if you step back and ask ourselves what we achieved by this, looking at the interplay between atoms and or between two-level systems, atoms in general, and photons, and the interplay with photons and other things, is that we came up with a very, very powerful theoretical methodology, which is called the theory of open quantum systems. Okay, so these open quantum systems, which are, as I said, which I mentioned, is a very powerful theoretical tool, is a method for understanding the interaction of a small system, such as an atom or a cavity, The cavity you can think of as confining a photonic field. An atom obviously is like a confined, system. And then with its environment, we want to understand this interaction of a closed small system with this environment, the external bath or the external reservoir, which could be an electromagnetic field, which could be other types of fields, etc. So this is the sort of big picture of what we think about in quantum optics. We have a system that we are trying to understand, we study. We may drive the system with various tools that we have available to us. Electromagnetic fields, voltages, whatever you want, will drive the system. And then the system will also be coupled to something that we call the environment. Okay? And this is the sort of the framework in which we look at a lot of problems in quantum optics. And that turns out also to be important for a lot of situations in quantum information science as well. This is sort of the key, the paradigm in which a lot of quantum computing experiments are carried out, right? So this coupled system can be reduced with very accurate approximations to solving equations of motion for the system alone. So essentially what we do is we call it tracing out the bar or removing the bar. But in the process of doing that, we introduce into the system things like decoherence, dissipation, etc., etc. And this is very vital for describing things like measurement, which has of course been a long sought goal in quantum mechanics, is understanding measurement and describing it more accurately. It used to puzzle everyone from Bohr and Einstein and so on about what is actually measurement. And also understanding something like decoherence. Why don't we observe systems in superposition states all the time, right? This is not to say that we have completely understood all of these problems. There is still valid fundamental research going on in all of these, but we now have a much more clear understanding of what the problems are and where we need to focus our attention. Okay? So here, for example, you have a cavity in which a photon mode is confined, and then the cavity can decay to the outside world, and we can also send in light from the outside world into the cavity. And so this is an example of an open quantum system. And we can measure the statistics of the light that is coming out of that cavity. Same thing here with this atom. We can measure the photons that are coming out of the atom, and we can look at their statistics. So these are the types of questions that we can ask about these systems. Okay. So where is quantum optics today? Well, really it is sort of blended into quantum information to a large extent. A lot of the fundamental problems in quantum optics now are really problems that are being studied or issues that are being studied that are relevant to understanding better quantum information science, quantum information processing, but it has been essentially defined in its connection to all these different experimental systems. Each of these experimental systems requires some slightly different modification or slightly different approximations of the fundamental quantum optics equations to understand it better. But so we have control now on systems at the level of single atoms, single molecules, single photons, single spin, etc. And we want to understand the coupling of these single atoms or single two-level systems with other systems like that or other electromagnetic fields. So that's typically where the connection comes to optics, which is the connection to the electromagnetic field, which is being coupled to this single atom, single molecule, etc. And then, of course, we can also use that to study many atoms, many two-level systems, many resonators, etc. That is among so here are all sort of these applications of quantum optics right now in things like quantum computing, as I already mentioned. We want to better understand how to control and engineer states in quantum computers. Precision measurement is a very, very important topic, which maybe is not talked about a lot but is actually one of the first has been one of the first applications of many of these ideas from quantum optics, such as in quantum noise and squeezing, and making more and more precise measurements of fundamental quantities. Of course, I don't need to tell you things like LIGO, which detected gravitational waves. That came from fundamental ideas of understanding quantum optics of light, which is circulating in a big interferometer. Okay, so and then also, as I already mentioned, fundamentals of quantum mechanics, probing systems, and then studying many body physics, which is a very hot area right now, using things like cold atoms, but also involving things like coupling of like many different qubits to each other, many different different types of systems that are out there for studying quantum simulation, for example. Okay, and so here's sort of a, if you like, brief overview of many different quantum optics and quantum computing systems. Everything from like electrons up there that are trapped in a two-dimensional electron gas and are being modulated by gates to create a quantum system. Some of these other things are things like nanomechanical resonators that are being coupled to light or to microwave cavities. We have the optics, ion traps and optical traps, atomic traps, and so on. Over there, clouds of Bose-Einstein condensed gases that are being put into a lattice for studying many body physics. We have defects in solid-state materials, which is sort of my research area, which are also very promising qubit candidate for many applications. We have NMR, which is the first sort of ways in which which is nuclear magnetic resonance of liquid molecules, in a liquid solution. That was one of the first ways in which simple quantum algorithms were carried out. And we have the superconducting qubits, which have become extremely hot right now as a way of doing quantum computing. I should mention there's of course other research areas in quantum computing now, things like topological quantum computing and measurement-based quantum computing. I'm not going to be able to talk much about that in this course. I'm still going to stick to the more, one could say, the things that came out maybe more in the 1990s and 2000s, and then the very recent work in the 2010s, so to speak, which is the topological and other types of measurement-based quantum computing. We can certainly assign those as topics to be covered in the presentations. Okay. That pretty much concludes this overview of quantum optics and quantum information. Any questions? Very quiet. Everyone's understanding everything. Okay. So let's jump into then a review of quantum mechanics. Lights here. Are there any light switches plugged there? I feel like the board is a little bit dark. Are there any switches back there? No. Okay. Hopefully you guys can see. All right. So of course, in quantum mechanics, we say that complete knowledge of a system is obtained if we know the wave function psi, right? Or the state psi, the state vector. And this is an element of the Hilbert space, right? Of the system and the universe, if you like. This is the Hilbert space of the universe. So if we know the state vector of the universe, we know everything, right? And but of course, a lot of times we're not going to try and understand the entire universe. We might expand, or we might construct some orthonormal basis, some of the Hilbert space or some subspace of the Hilbert space of the universe, and we can write an expansion in terms of this orthonormal basis, which is n is a basis of this Hilbert space, right? And so then we get these expansion coefficients n psi, which you might sometimes define as Cn, right? So the coefficients, expansion coefficients of the state in the basis n. Also, you should probably recall that the state psi is actually in the Hilbert space. You can think of it as a ring, right? So it's not just a vector alone. For example, the state psi and the state alpha psi both represent the same state of the system, right? They're not different states. We don't worry about them being different states of the system, okay? Where alpha, of course, can be a complex number. So, okay. The probability, this is the famous Born rule, is the probability of finding the system in the state n is then simply the Cn squared, right? It's just this coefficient modulo squared. And this gives rise immediately to the first effect, which is superpositions and interference. Which is this property that if you take the system, if you have two states of the system or the universe which are, you know, which are both expanded along this orthonormal basis, and we have another state psi 2 which is expanded along the same. I've just used some dummy variables, or let's just call it that. Then, okay, then if you take the superposition psi 1 plus psi 2, what you find is that the probability now Pn to be in the state n is no longer just the sum of the probabilities, right, of 1 and 2. Okay, so yeah, I mean, so this is obvious, I'm sure, to everyone, but we'll just write it out. Which is Pn of 1, which is modulo Cn1 squared, and Pn of 2, which is Cn2 squared, right? And then the probability of being in the state n when you are in that system state psi equals psi 1 plus psi 2. So now psi equals psi 1 plus psi 2, and if you want to be careful, you can divide by square root of 2 and so on. Then the probability to be in the state n now is given not by the sum of these two probabilities, which is how most normal probabilities would work, but instead it's given by the sum squared of their amplitudes, right? And that gives rise to the interference term. If you carry out that calculation. calculation. And the interference term is Cn1 star Cn2 plus Cn1 Cn2 star. Okay, right? And this is a very important, obviously, gives rise to most of the effects in quantum mechanics that are counterintuitive. Okay. Okay, so now we have talked about probabilities, but usually what we are observing in experiment, in any experiment, is not the wave function or the state kept directly. We are observing some physical variable, position, momentum, energy, the magnitude of the intensity on the detector, etc. So we don't observe these directly in the state kets. Instead, we are looking at some observable, which is defined as an operator, right, in the Hilbert space. So, observables in quantum mechanics, these are Hermitian operators. On the states of the Hilbert space. Okay? So, a Hermitian definition, just as a reminder, is that the these are, when you interchange the indices, you get the complex conjugate of the this expectation. Okay, and the expectation value then of the observable O is simply, when the system is in the state psi, is this quantity. Okay, and if O is diagonal in that orthonormal basis N, then we have that O acting on N gives you some value, complex number maybe, but of course, as we know, for Hermitian operators, these will turn out to be also real numbers. Okay? Again, I'm not proving many of these statements. This is just review of things you know from quantum mechanics. And the expectation value then quite simply becomes this quantity here, On times Cn squared, modulo Cn squared. And Cn squared, remember, was the probability to be in the state N for the system, which is in the state psi. Therefore, we know that this can be written as something that's much more analogous to classical or standard probability theory, which is, in standard probability theory, if you want to calculate the statistical average or the statistical expectation of some variable, you will want to know all the probability for the system to be in that state, or in that particular case. So you throw a dice, say 10 times, and you want to know what is the expectation of, say, 5 heads or 6 heads or something. Then you will calculate the probabilities to be in those different states, N, and then multiply by the value of the observable in each of those states, and then you will calculate the expectation value of that observable, right? So this is the standard way to calculate expectation values in statistical physics or in statistics, and in quantum mechanics. Also, at this first level, when the system is just in the simple, is diagonal in the basis n, then we immediately get again an expectation value that is just simply obtained by taking the value of the observable times the probability to be in that state and summing it all. Okay, so that was hopefully simple. And also, of course, the other thing we should note is that if we have a system that is starting out in, say, the state m, and we observe the value on, and then we repeat this measurement, right, we're going to get the same value on. It won't change. Okay, so it's not true that in quantum mechanics that always measuring the system destroys the observable. As you see, when you collapse it into an eigenstate of the observable, then you're going to keep, and you repeat the measurement, you're going to keep getting the same state back again and again. Okay, so that's another thing to that we should all know by now. Okay, so last part before I go into something a little different from what you might have seen earlier, just reminding you that the uncertainty principle comes about because operators do not, right? So if you have two operators A and B, you have two operators A and B, and the commutator is some third operator C. Okay, then if C is not equal to 0, then A and B do not have the same eigenstates. And this is where we start to get the problem that if you measure one of these observables, then the other one is collapsed into some superposition of its states, and therefore you cannot get a definite value, or the uncertainty in that value changes. Okay, so then from this relationship we can derive the Heisenberg uncertainty principle, which is delta A times delta B is greater than or equal to I over 2 times the expectation value of C, where delta A is defined as the statistical quantity, which is square root A minus A expectation squared expectation. Okay, and delta B is defined similarly. Okay, again, stuff that you've all seen in quantum mechanics. So that brings us now to the important thing that we all care about in any quantum information system or quantum computing system, which is time evolution. Because typically a quantum computer or quantum information processor, etc., you set it up and you let time go from left to right and watch the computation unfold. So we need to understand what happens to a quantum system as time evolves in the computation or in any particular physical process. So time evolution then is the first thing that we need to write down. Again, this is mostly review, but I'll start introducing some new stuff at the end of this. Or maybe it's new, I don't know. Maybe you guys have already seen it, but we'll discuss that. Yeah, I can go faster. Well, I should start moving these boards around so I don't erase stuff out. So time evolution the first way in which we look at time evolution, which is the first way in which time evolution is introduced in quantum mechanics, is in what we call the Schrodinger picture, right? And that comes through the Schrodinger equation. which is IH bar dou over dou t times psi is equal to H hat times psi, right? Where H hat is the Hamiltonian of the system. Okay? And typically you'll get the Hamiltonian typically from some classical analogy to the dynamics of the system or to the energies of the system. But we want to define it in this general way, where H is the Hamiltonian. And so what we can think about is H is the Hamiltonian that generates time evolution of the system. H is the operator that generates time evolution. By knowing H, we know how the system evolves in time. Okay? And the important solutions, as we have already mentioned, we find the stationary solutions, right? Stationary because the probability, once you are in this state, the probability does not change once you are in that state, right? And that's because Hn times En equals En is an eigenvalue of the Hamiltonian, right? So if we expand any state psi in eigenstates, let's say at psi at time 0, we expanded it in eigenstate in terms of these eigenstates of the Hamiltonian, right? Then from these equations we can derive that psi n at some time t is equal to summation n e to the minus I e n t over h bar times Cn times E, right? And so if you started, of course, in the state, say E1 or E2, whatever, ground state or excited state, etc., then the probability will only be multiplied by this phase factor, e to the minus I E n t over h bar, which means that the probability to be in that state will not change, okay? It will stay in that state as time goes on, okay? Because the modulo squared is still the same as the original Cn. Okay? And then if you are in a superposition, then of course you're going to get interference terms of all those different states. Okay. We can also formally integrate this equation. Okay? This equation here, I can imagine that it's just like any other equation, and I can integrate it in this way, right? Psi of t is equal to exponential minus IH t over h bar, okay, psi of 0, which I will define to be the time evolution operator. Okay, so time t from 0 up to t is the time evolution operator. And we can know what this operator looks like if we expand it again in the system where we know that H itself is diagonal in its eigenbasis, right? So if we write H as a matrix, right, with these in this expansion, this is a matrix, and in that matrix expansion, En will be on all the diagonals. And therefore, this exponential can be easily evaluated, right? Because the exponential of, this is a matrix now, so we have to do matrix exponentiation of this system. So that's how you can think about like what would actually be involved in calculating the time evolution operator, is that it's the equivalent to exponentiating a matrix, right? And that's something that's well known how to do. Okay, now we have introduced the Schrodinger picture because that's how time evolution is normally carried out, and I've written down the time evolution operator there, but I want to now introduce some other pictures of time evolution. I will leave this up here. Maybe I'll just write down the time evolution operator. T 0 is equal to e to the minus I ht over h bar. Okay, and now I will introduce the Heisenberg picture, which probably you've also all seen. And the interaction picture, again, this is all, review of things you would have probably learned in quantum mechanics. Everybody has seen this? Interaction, Heisenberg pictures and stuff, right? Okay. So in this picture, the state vector describing the state of the system does not evolve, right? The state vector stays the same, and rather the observables that are describing the measurements on the system, the things that we are interested in, that we are actually looking at, the physical variables, those are the things that are evolving, okay? So they depend on time, and they evolve according to Heisenberg's equation of motion. Again, I'm not deriving any of this, but I'm just saying that in this picture, it's the observables that change. So notice that in the earlier picture, when I calculated the probabilities, it was all the time evolution was built into the system, into the coefficient Cn, for example. Okay. So in this case, the time evolution is built into the observable itself, and this can be helpful, as we'll see later on, when we are dealing with different types of forced harmonic oscillator or different types of driving of systems. Okay. And so if you take an eigenstate of this observable, of O. So notice now that this is an eigenstate of O, which is not an eigenstate of H, not necessarily an eigenstate of H, the Hamiltonian. Let's call this eigenstate L, Lj. Or maybe I should have called it O, but I'm just choosing a slightly different symbol here, L. Okay. Okay. So Lj is an eigenstate of the observable O with an eigenvalue Lj. Okay. Then remember we had introduced this time evolution operator T, right? Then if you substitute that, you will find that these eigenstates of T of the observable O will transform according to the time evolution operator in backwards fashion. So going from T back to T naught or 0, whatever you want to call it, T back to 0 times Lj of time 0. Okay. Or equivalently, you can say that Lj at time 0, eigenstate, will transform and I put this over bar over these guys here, sorry, I forgot to put the over bar here. They represent the Heisenberg versions of these basis states. Of course, at time t equal to 0, the Heisenberg states and the regular Schrodinger states will coincide with each other. If I now differentiate that equation for the eigenheads of O, I'll get a differential equation for the for these eigenvalues. Okay. So let me differentiate this equation, right? This one, sorry. Then I get d over dt of t0 times Lj of t with the over bar. And then I pull over that guy to the left hand side and differentiate that. E of t0, d by dt, Lj of t over 1 equals to. Because this guy on the left hand side, if this is the ket at time t equal to 0, has no time derivative, right? The one at time t equal to 0 is constant. So its time derivative vanishes, is equal to 0. Okay. Then using the time evolution operator's definition, if you substitute that back in here, we get IH bar d by dt Lj of t is equal to minus h Lj of t. So remember in the Schrodinger picture, when we looked at the evolution of the state ket, it evolved with a plus sign for h, right? That's the definition of, that's the Schrodinger equation, right? The Schrodinger equation, the state ket rotated with plus h times psi at some other time. Here, the observable, right, and its corresponding eigenstates, right, the eigenstates of the observable are rotating in the opposite sense from the Schrodinger picture. That's the basic thing, because we get this minus sign for the time evolution of the eigenstates of the observable. Okay, because any observable, right, in its eigenbasis L1, L2, etc., say Lm, will be diagonal, right? And what I'm saying is that as we evolve in time, that this is going to now come in with a minus sign on the Hamilton. Okay? So as we evolve, this operator in time is going to have this opposite behavior from the Schrodinger states. Okay, moving on to now the final picture, which is the interaction picture that we'll use. If you didn't follow the derivation again, I mean, you know, it's something you can review from your textbooks. So in the Schrodinger picture, we put all of the time evolution into the state vector, and the operators are just standing still. And then at the end, when we want to calculate an observable expectation, we just take the operator and sandwich it between the eigenkets or the state vector, right? So psi of t is varying with time, and O, the observable, stands still, has no time evolution in the Schrodinger picture. In the Heisenberg picture, what we have said is that all of the time evolution is in the observable O. So O in this guy is going to evolve in time. So it's going to have some change as time goes on, and the state ket psi of 0 is whatever it was that we initially prepared the system at the beginning, and we'll imagine that we see observables that are changing. In the interaction picture, we're going to do a hybrid of both of those. Okay? And the reason for that, of course, is because we're going to have the system which is being subjected to some forces, for example, and the forces may be time dependent, and initially the system, we understood the system very, very well without those external forces that were acting on it. Okay? So what we want to do is we want to get rid of any of the trivial time dependence, the time dependence that comes from the things that we understand very well. As an example, let's say a harmonic oscillator, we understand very well what the time dependence of that system is. Okay, we know all the details of the harmonic oscillator, how it's going to behave, but now imagine that we force it, we apply some forcing term to it. Okay, then now we want to focus only on the part of the system which is due to the forcing, and not worry about all the stuff that came before that, which is the part that we understand very well, which is the fundamental Hamiltonian of the harmonic oscillator. So we write the Hamiltonian H as having two parts, H naught plus V. Okay? And in general, both H naught and V can be time dependent, right? Both H naught and V could be functions of time. Although more typically H naught will be time independent and V will be the time dependent part. Okay? Okay, so I'm debating whether we should go through the whole derivation here. Why don't we stop here with the interaction picture, and I'll come back to it in the next class. So this is probably one of the most important pictures that we'll be using a lot in quantum optics also, because as I've explained already, in quantum optics we're going to have systems, for example, like an atom, right? And we know the fundamental Hamiltonian of the atom, H naught, very, very well. So we're going to divide up the system as having a part which is H naught, and then a part which is V, which is the whatever perturbation that we are doing to it, which may include things like interaction with the environment. And we will want to understand more specifically what happens to the evolutional system under the action of these perturbations. Okay? And that's why we use this interaction picture a lot. So I'll come back to that, or maybe I can even just distribute the notes, because this is probably something that you're all quite familiar with, and I don't necessarily need to go through the derivation of it very carefully. Instead, what I'll do maybe is just start with an example in the next class of how to apply the interaction. And I'll give you guys the notes of the interaction picture derivation, because it's something you probably have seen already. So, all right. Okay, so we'll see you all in the next class. Anybody else didn't get syllabus? Oh, actually, we have a few minutes, right? I didn't get to know any of your names. Can we quickly go through and I'll just get to at least know who was in the class. Why don't you sit back down? Sorry. Very bad. Oh, I made you come back. Alright, why don't you just go around, tell me which year your name, which year you're in, and if you're working in a research group or not. I'll start with you.
I'm Pinglei.
Yes.
30 years. I'm working with microhydration.
Okay.
I'm Chao. I'm second year, and I'm also working with Dr. Hydration.
Okay.
I'm Zhikang. I'm working with Dr. Patek.
With Dr. Patek?
Yeah.
And which year are you in?
Third year.
Third year. Okay.
I'm 30 years. I'm working with Dr. Patek.
Okay.
I'm Namita. I'm in third year. I'm working with Dr.
Oh, okay. Cool.
I'm Evan. I don't go here. Just working.
He's undergrad. Yeah. Okay.
I'm Srini. I'm a third year. I'm with Dr. Lali.
Okay.
My name is Paul. I'm the fifth year. I work with Soviet law.
Okay.
Tom, I'm in my 7th year. I'm working with Dr. Silverclough.
Okay. I know you, but okay, introduce yourself.
I'm Chen Xu from Professor David Packer. I'm Professor of Research Group, and this is my 6th year.
I'm Bela. I'm just auditing the class.
Okay. Thank you. All right. Thanks. Great. Hopefully, I'll try to get to know.